now we're going to find the volume of a solid by using a shell. So a shell you can think of as the lining in your hydro flask. We're going to be finding the volume of that. So what we're going to do is we're going to say, okay, take the circumference, 2 pi radius, and then give it height, and then I'll multiply times the thickness, of course, which will be our dx. We'd add a bunch of these up, let the number of them go to infinity, and there it is. So x is the radius of the shell, and f of x is the height. So this is a graph I don't expect you to know, and I would never put this on a quiz or a test. But this graph here crosses here at 0 and 1, and I wanted to use this as an example of why we need shells. So if I'm going to be revolving this area here about the y-axis, there's no way that I could draw the rectangles perpendicular to the axis of rotation because they would touch the same function, top and bottom. That's not a possibility. Okay, so I'm going to have to draw the rectangles parallel to the axis of rotation. So parallel rectangle like this, and I'm going to spin that around. Can you see the shell? Yeah, okay. So parallel rectangles for shells. Just need to remember that. Discs and washers, the rectangles are perpendicular to the axis of rotation. So here we go. So 2 pi, and then I'm just going to put blanks here for a second, and I want to put the dx down because we want to remind ourselves we're doing dx integration, and that's because the thickness of this rectangle that I've drawn here is dx. So in this spot here, I'm going to be putting the radius. So let's think about that. So the radius of this one shell. So remember, the integral is going to like add up a bunch of these rectangles doing the same thing. So this radius from here to here would be an x value. And then if I was to do another rectangle, that would have a different x value. Well, this integral thing moves that x value around. So we're literally going to put an x there, and the integral will move around, and this is 0 and this is 1. It will move the different radius. Now I'm going to find the height of the rectangle. Oh, well, that's just the function. In this case, it's going to change. So this is the height. So 2 pi radius height, and then dx gives us thickness. That finds the volume. All right, so this is more of what you can expect on homework test quizzes. So x squared plus 1, parabola shifted up by 1, like that, right? And it's useful to have colors. So I'm just going to change colors here. Y equal x. Then we have x equal 1. So I know it crosses both of those, right? And x equals 0. Okay, so I need to make sure I'm looking for the area that's bounded by all of these. Okay, so mistakenly, you could think it's this area here, but it's not, correct? Because that's not bounded by all of them. Actually, let me make this x-axis and this y-axis. Well, yeah, there's a y-axis. So it did not say y equals 0. So the x-axis is not being used to find the area bounded. So if I'm looking for the area contained by all of the graphs, it would look like this. Okay, I'm going to be revolving it about the y-axis. So that's the center. And so can you see, if I try to draw rectangles perpendicular to the axis of rotation, I would have different top and bottom functions. That is not a wise choice. I'm never going to ask you to do rectangles that way because you'd have to split this volume up into a couple, at least 2 different integrals. So I'm hoping you'll make the wise choice and say, yes, I want to draw my rectangle this way. The top here and the bottom is the red one. And if I spin this parallel rectangle around the y-axis, you see the shell. It looks different than a washer. So it's going to be 2 pi radius height, and I see that the rectangle is of width dx again. So radius will be just like we talked about last time. It's going to be some x value, because the center is the y-axis. Go up to some x value, that's the radius. Then the height. This one's a little more tricky. So the height of this brown rectangle here, top minus bottom. So it's going to be the green parabola, the x squared plus 1. Subtract off the red line minus x. And so all of that is the height. And where am I building these rectangles from and to? I'm going to start building them at x equals 0 and keep building them to x equal 1. Okay, let's try another one here. So y equals square root of x. Square root of x, looks like that. Y equal x looks like that. Okay, so this one, let's think about what the area contained is. It's right in here. So this does not say use shelves. So I could actually do both ways. I could make rectangles parallel to the axis of rotation or perpendicular. So let's start with parallel. So if I'm going to make my rectangle parallel to the y-axis, because this is what I'm spinning around, right? It's a good idea to understand where center is. If I draw it parallel, I get a shell. So it'd be 2 pi integral, and then I'm going to put in the radius and the height, and I see that it's dx integration. So radius, again, is just an x value, right? So this x distance from the center out to where I build the rectangle. And then the height will be, let's look at it, the height of that gray rectangle, top, root x, subtract bottom, x. And then where do I build these rectangles from and to on the x-axis? Well, I know that they're going to intersect at 0 and at 1. So let's just, since it didn't say, this would be totally legit to draw the rectangles another way. So let me just draw the graphs again. So I'd have root x and y equal x. And so still spinning, I'm not changing the axis. But if I want to draw the rectangles perpendicular to the axis of rotation, I can see that this is going to be a washer. So washers and disc, that rectangles are perpendicular to the axis of rotation. So let's get the framework set up. So it's going to be outside radius squared minus inside radius squared, and it's going to be dy integration. So remember, this is really useful to put down near the beginning. Okay, so this is the center. So center out to the green line is the outside radius, right? So you might be tempted to say, oh, that's the y equal x. Oh, but I have to do dy integration. And so that means I need to put y in there. So there's y. And then I'm going to be subtracting off this distance from here to here. Oh, and what's that? That's going to be the root x. Again, you might be tempted to put root x in there. Then this reminds you, you have to put it in terms of y's. So if I take this and solve it for y, solve it for x, so I get that in terms of y, so I'd have x equal y squared. So y squared. Okay, so now these limits of integration have to be y values, right? So let's think about it. This is 0. Oh, yeah, it would be 0 to 1 on the y-axis as well.